All right, so welcome everybody. That's the last installment of the Global Poisson webinar in 2022. We already have a full schedule for winter spring 2023. And I think the first talk will be on January 26th. So there will be a winter break, and the webinar will restart on January 26. We'll send you the announcement and we'll put online the full program. And today we are very happy to welcome Leon Takhtajan, who will be speaking on supersymmetry and trace formulas. Leon, I give you the floor.
Okay, thank you very much, Anton. Thank you. So that's the title of my talk. It looks like it has very little to do with Poisson, but we'll see, that it has something in common. So the title of my talk is Supersymmetry and Trace Formulas. So let me start with a very brief and gentle introduction. So what I mean by trace formulas, it goes back to computing indices. So the main object introduced in early 80s by Ed Witten is the way to interpret different localization theorems and formulas for the indices of certain operators, for indices for certain complexes, and so on. So basically, the idea is very simple. We consider the graded Hilbert space, just Z2 graded, and you may think of it as a Hilbert space of some supersymmetric quantum theory, but it's pure mathematical notion. So I will use these physics words, but you can ignore it. Because actually my co-author, Changha Choi, he is a physicist, high energy physicist. So what I will talk about is in this paper on the arXiv. So that's the paper. So what we do since we have a supersymmetry, there is a number of particle operator, and so there is a parity, plus and minus, which is represented by e to the negative f operator, which is plus minus 1. So you can think of operators in Hilbert space as 2 by 2 matrices in according to the grading. So the supertrace means not the trace, some of the traces along the diagonal, but the difference. And so with an index, you have some operator h bar. Think of this as a Hamiltonian operator. Then this written index is the supertrace of this operator, is the ordinary trace of Euclidean evolution operator, e to the negative beta h bar, multiplied by -1 to the power f. So if you, as I said, represent this operator e to the negative beta h bar as a 2 by 2 matrix, so call it A11, A12, A21, A22, then the ordinary trace of this operator will be trace A11 plus trace A22, whereas the supertrace is the difference between traces A11 and A22. So it's that simple, but you use all these fancy words just to make it sound nice. And then, of course, the key thing is, can we compute this thing, the index? If the operator, if the theory is supersymmetric, then there is a certain basic object, the supercharge, so which satisfies certain algebra. I will not describe it. It depends how many supersymmetries you have. For the simplest case, n equals 1/2 supersymmetry, we have only one supercharge q bar, which is an operator in the Hilbert space H, and then supersymmetric Hamiltonian H hat. It's just q hat square. If you, of course, all these words mean that q hat is a Dirac operator. That's all it says. And then the basic fact, if our h hat is q hat squared, is that Witten index doesn't depend on beta. And that's the crucial thing. Then we may set beta to be 0 or beta to be infinity, and then we can get some different expressions for the index. Let's consider the simplest example, which is discussed. So you have a Riemannian manifold M with a Riemannian metric. Then you have the following Lagrangian, supersymmetric Lagrangian. It's a particle on Riemannian manifold with this kinetic term, plus there is a supersymmetric contribution. You have some fermions. Fermions are just tangent vectors along the loops with reversed parity. And then this nabla x dot is a Levi-Civita connection. And then there is a standard supersymmetry, which replaces bosonic coordinates x mu and fermion coordinates psi mu. And it is described by supercharge. I didn't write it here, but here everything can be explained in terms of graded Poisson geometry. Namely, you think of Q as observable, and then what is delta x mu? It's just a graded Poisson bracket between Q and x mu. So that's how graded Poisson geometry appears in the supersymmetry. So, because these are classical formulas, so this is just Poisson geometry. Then, when we quantize it, effectively, we replace graded Poisson brackets by graded commutators. And then corresponding supercharge, classical supercharge, becomes quantum supercharge Q hat, which is just a Dirac operator. And one more Poisson formula, that classical Hamiltonian H is a Poisson bracket between Q and Q. Since this is a graded Poisson bracket, this is not 0. So that's the relation with Poisson geometry. And so quantum supercharge, then we get written index. It's just the index of a Dirac operator, which is an integer. Then it can be written as a path integral over bosonic and fermionic degrees of freedom, where we are integrating, so to say, over the tangent bundle to the loop space of the manifold with reversed parity.
Can I ask you a question?
Yes, sure.
So in the Lagrangian, the second term means, so as far as I understand, this is the first term is scalar and second term is not scalar because index mu nu is there and there is no metric or some other thing like epsilon.
Oh, sorry, G mu multiplies them both. Sorry. That's, thank you. That's a typo. G mu multiplies them both. So then there is another question. Then if it is G mu nu, then this is a Levi-Civita connection and it acts on the spinors. So as far as maybe I'm wrong. So this Levi-Civita connection, there is some spinorial analog and there can be many spinorial analogs. So can you be more specific? Psi mu are tangent vectors. Psi mu are tangent vectors with reverse parity. Just so no spin, tangent vectors. So everything is fine. Thank you for commenting on the typo. Okay. So we have this. Now it is given as a path integral, Euclidean path integral. Actually, one can try to make mathematical sense out of it, like Jean-Michel Bismuth does it, but it's really very far beyond what we are discussing today. And so then the key thing, the supersymmetry, is that classical action, Euclidean action, is delta of some other function, of some other functional. So that if you apply delta supersymmetry transformation to the action, you'll get 0. So this means the theory is supersymmetric. And then the key fact is that this written index can be written, this integral can be written as, you can add arbitrary deformation delta v for any functional v such, and then this will not depend on lambda. Then,
Leon?
yes,
Sorry, here I got a little bit confused. So SE is equal to delta V, or like, is it the same V in the two lines, right?
yeah,
Because
in this case, it's the same. You see, for this particular example, for the Dirac
it's not
operator.
necessarily, right? You
Yeah,
can,
yeah, but it's necessarily so. But you need to add some. You need to add other delta V. All you need delta SE to be 0. This is supersymmetric. But it happens that in this particular case, SE is delta V. If for some V which we are not, which I will describe later.
there is also a comment on the chart where Dima Reutenberg is saying that psi I should be understood as dxi. Is it right? I don't know whether you see the chart.
Yes, they are tangent vectors too. They are tangent vectors.
So
Components of tangent vectors. Tangent vector is psi.
Yeah.
Then you expand it with in terms of the basis, right?
so more like d over dxi.
Right. Well, psi mu times d by dxi mu is a tangent vector in the chart.
Okay, thank you.
So we have this. And then the key fact is that this integral doesn't depend on lambda. We compute in a limit when lambda goes to infinity, and then everything localizes at the zero locus of delta V. But delta V is SE, so we need to look at the zero locus of Euclidean action. If we come back to the Lagrangian, then the zero locus is where kinetic term is 0, which means constant maps, So everything localizes on zero locus, constant loops, and then it is computed. That's Atiyah-Singer index formula in a very brief way. So that's how people understood it, starting from Ed Witten. I think this computation was first done by Alvarez Gomez, following these ideas of Witten. And then Atiyah was very much excited by all this development, and he wrote a very nice report, I think in a seminar Bourbaki or somewhere, about this approach. Of course, all this can be phrased pure mathematically as just in terms of equivalent cohomology, in terms of usual localization theorems, in, say, infinite dimensional. And one can state an elementary finite dimensional example. So when you consider S1 action on a manifold, V is the vector field of this action, you consider equivariant differential, capital D, D square is the derivative along the vector field. Then the very simple lemma says, if you have a differential form, which is capital D closed, which is equivalently closed, so it has several components, and you have some capital V is a equivalent one form along M, then integral of this equivalently closed form alpha over the manifold, you can perturb it by this exponent, you get the same integral. And that's the key when lambda is 0, you get the original integral you want to compute. When lambda goes to infinity, this term becomes zeros of dv, become dominated, and you can compute this integral exactly in the limit. It's in this Euclidean formulation, just Laplace method of evaluating steepest descent. Or you can put imaginary lambda, then you get stationary phase approximation. And the proof is very simple. Since here it is explained, since d square v is 0, then the top component of alpha is little d exact, and then integral localizes on 0 locus of dv of, you take dv, zero component, which is a function, and you consider its zero locus, and the integral localizes. Zero locus may consist of isolated points, then you get sum over these isolated points, or it may be some manifold or union of varieties, then you get certain integrals. All this is described in a book by Berlin, Getzler, and Verne pretty clearly. So all this was just a warm-up, because I am not discussing this. I am discussing trace formulas. And so the question is, we can compute in certain cases, we can compute the Witten index, which is very nice because it captures all results from Atiyah-Zinger theory. Say. Now, can you compute the actual trace of Euclidean evolution operator? So this is the question. Of course, this sounds a little bit crazy, since Witten index, in many cases, is just an integer.
Can I ask another question?
Yes, sure.
If lambda is positive, then if lambda is negative, then it is kind of divergent, no? This integral.
Lambda is positive. In this case, lambda is positive, goes to plus infinity.
No, it's written lambda belongs to R, so that's why I asked the question.
Right, but you see, M is compact manifold anyway. In this is a baby example. This lemma is a math lemma. It's a baby example. M is a compact manifold. Okay, so let's return to the main question. How to compute the actual partition function? The trace of Euclidean evolution operator has a physical meaning of a partition function. And this beta has a meaning of inverse temperature. It's not important for us, but just for people who think. And then, well, it looks crazy because you cannot compute the trace of any operator. Of course, there are basic examples when you can compute. This include from the most difficult one, Selberg trace formula. Then the easier one, we call it Eskin trace formula. And then of exact computations of a trace. Gutzwiller did semi-classical approximation to a partition function, which is pretty standard elementary physicist approach. You consider like the limit when like h bar goes to 0, there is a semi-classical approximation for the evolution operator, and Gutzwiller mimicked this for the partition function. Sometimes it's called Gutzwiller trace formula, although it's a semi-classical. It's not exact. Selberg and Eskin are exact. Then there is what is called Poisson trace formula, or Jacobi. It's better to say Jacobi-Poisson trace formula, which will derive. It is also exact, and of course. And the key here is the following slogan, that the spectral trace equals to the metric trace, to the matrix trace. This we know well for matrices. Spectral trace is the sum of eigenvalues if a matrix represents a semi-simple operator, if it's diagonalizable, or even if not. And then the matrix trace is the trace of a matrix, and they are equal. This is what we teach in linear algebra. And then it turns out in this path integral formulation, spectral trace is operator trace. It is a definition of a partition function. Trace of e to the negative beta h hat. Now, what is a matrix trace? Clearly, the matrix trace is a path integral, because that's how Feynman formulated the path integral for the propagator, for the kernel of, for the integral kernel of the evolution operator. And then if you integrate, and then if you take the trace of the evolution operator, meaning initial and final points are same, and you integrate over all this variety of these points, you get a path integral over a loop space. And there is one thing I forget to say, which is fundamental. When we write index of Dirac operator as a Euclidean path integral, we have a loop space. It means, and this is for the thing is the following. If you consider trace for bosonic variables, it means periodic boundary conditions for Bose variables. Trace for Fermi variables means anti-periodic boundary condition for the path integral over Fermi variables, Berezin integral. And so, but if you consider supertrace with respect to fermion degrees of freedom, then you get periodic boundary conditions for both. That's the key fact used everywhere by physics. So in this formula, which I am underlining here, the fact that I, capital I, is supertrace is fundamental, because supertrace gives you loop space of a manifold. And then you may ask, how can we do the actual trace? Because actual trace naively involves periodic boundary conditions for bosons and anti-periodic for fermions. Now let's, and you see, remarkable thing is that there are cases when you can apply the same localization principle when to compute the trace, the partition function. When this happens, when can you do it? You see, if supertrace is not zero, you cannot compute the trace. For instance, take a Dirac operator. Supertrace is just the index of a Dirac operator. It's invariant. It doesn't depend on the choice of a Riemannian metric. But can you compute the trace? Obviously, no. But then if the index is zero, then, and you have fermion zero modes, then, and if the fermion zero modes decouple, then you can compute actual trace also as a path integral over the tangent bundle to the loop space with reversed parity in the fibers. So you see, idea is kind of very simple. If your e to the negative, as we discussed, your Euclidean evolution operator is a 2x2 matrix, block matrix, right? Where all A11, A12, and so on are operators. A11 maps H plus into H plus, and so on. If the index is zero, means trace of this operator equals to the trace of this. And so, and then if they are equal, there is a chance we can compute their sum. If this is, this zero is due to the presence of fermion zero modes. Fermion zero modes mean that the path integral over fermions vanishes identically by the following reason. All this is built on Berezin integration. Namely, Berezin integration in its simplest way is the following thing. You say that if psi is a Grassmann variable, d psi is zero, and psi d psi is 1, where you have 1 degree of freedom. If you have several Grassmann variables, psi 1, psi 2, so on, then you get the same formula that d psi I is 0 and psi I, d psi I is 1. And then you can kind of consider multiple integrals using this. You can compute all multiple integrals, because actually integral over Grassmann variables is rather a differentiation. Berezin integral is a differentiation of polynomials of elements in exterior algebra in some precise sense. So if it happens that when we are integrating over fermion zero mode over fermions and one fermion is missing, then we get identically zero by default. And this means that there is a fermion zero mode. And this is the case when one can try to compute the trace instead of supertrace. So let's state there is an elementary example which we put in a paper. Maybe I should skip it for them just and try to give you instead. There is elementary finite dimensional example, which basically says, let me say it in words, you have some equivariantly closed form, which if your manifold is a product of two, say, if your manifold is product of another manifold by a circle, and you have equivariantly closed form on your base manifold, and it doesn't, and its differential doesn't contain coordinates on a circle, then integral of this equivariantly closed form is automatically zero because you are missing one dx, right? But then if you multiply your equivariantly closed form by this dx, which is missing, then you get the total integral, which is non-zero. And then you can do a localization. That's very rough description. I don't want to discuss it. I like to state you localization principle in general form. Yes.
Just a short question. So there it was a direct product with a circle. It probably can also be an S1 bundle in the previous example?
Yes, of course, yeah, because you see, in usual localization principle, we have a nice finite dimensional example, right? That's just equivariant cohomology. Here, we also write this finite dimensional example, which is more primitive, because vanishing of the integral of a manifold of a form of a manifold is trivial because form misses one dx, right? That's all. So automatically the integral is zero. So because form is of a wrong degree. But if it misses just one component, then you multiply it by another one form, then you get a non-zero value. And then if everything is equivariant, you can compute it. You can still do a deformation. You can add this V. But instead of discussing this in details, finite dimensional example, let me formulate the principle. And then we'll get Jacobi Poisson trace formula. That's what we'll get. And then, of course, I'll sketch other things. So now, this is the formulation of this localization principle. So we have system, supersymmetric system, say supersymmetric quantum mechanics, because we have n supersymmetry and curly n is 1/2, so just quantum mechanics thing. And suppose that Witten index is identically zero due to the fermion zero modes. Suppose there are n of them, so that in Bayesian path integral over fermions, over Grassmann variables, d chi1 and so on, d chi n are, you need to integrate over d chi1, d chi n, and this variables chi1, chi n are missing. Therefore, index is trivially zero. Then the second condition, that in a quantum theory, you consider, you quantize these classical modes, you get actual fermion operators, it's finite dimensional space, suppose n is even, their product is gives precisely the parity operator with this coefficient. So this kind of nature. Then another condition is very important. So we have a supersymmetry, and still, if you apply supersymmetry transformation to each of these fermion zero modes, then the zero mode x mu is missing in this. In other words, Bayesian integral delta chi mu d chi mu is zero. So this means that variation, or when Poisson bracket, if you like, q and chi mu, Poisson bracket, doesn't contain chi mu. It means precise statement. This is delta chi mu. So this means that delta chi mu doesn't contain fermionic degree of freedom chi mu itself. And then we have the following locally, then deformation. Suppose that capital V is a functional which is such that delta square of V is zero, which we required for the deformation because we are adding delta V. And moreover, that V and delta V also do not contain fermion degrees of freedom chi mu. Looks very, very special. Then,
John,
yes.
just a question. So this something orthogonal to chi mu in another language, does it mean that it's basic?
Well,
Right.
it's just a shorthand notation. This may be not the very good notation. Delta chi mu orthogonal to chi mu. It means precisely that Bayesian integral delta chi mu d chi mu is zero. That's all it means. Yeah. So kind of it doesn't contain fermion degree. This degree of freedom is missing. If you expand.
But you would agree, right? This formulation doesn't contain something is not like it's probably right. Some contraction operator acting. It's in the kernel of some contraction operator. Is it?
Yes, of course. Yeah, you should write it. Yeah, you can say it in words. But to write it, yes, you can write it as a contraction operator. Yes.
Okay, thank you.
And then just let's look at. Let me make it. Let's look at this integral. We have a supersymmetric theory. So SE is Euclidean action. It's supersymmetric, but we added a product of observables. Chi1, this is a path integral. So we added a product of observables. And these observables, this is invariant under supersymmetry transformation. This product is not. So we are integrating a non-supersymmetric object. Therefore, usual localization principle doesn't apply. So you cannot compute it by a usual localization principle. But if deformation, call this capital V as deformation, if deformation V is such that this holds, which is standard, this is standard, and these conditions hold, which are new conditions, then this path integral still lambda independent. And then when we send lambda to plus infinity, the path integral will be still will be localized, still will localize on the zero locus of delta V. And how to find such V? In examples, it turned out that in examples, this V contains higher order derivative terms. Therefore, delta V, zero locus of delta V is zero, actually gives equations of motions, not constant loops like in a T-Singer. Constant loops are also very, very special solutions of equations of motion. But equations of motions are second order. Therefore, this V, and that's the goal, to localize not on constant loops, like every equivariant cohomology theory does, but localize on classical trajectories, on solutions of equations of motion. And then the proof is very simple. It's a formal proposition. So this is the main thing. So we can compute certain path integrals of non-supersymmetric observables by localization, provided the deformation and this observables chi1, chi-n satisfy all these conditions. So all these conditions are crucial. This one, orthogonality, and this conditions. And then it becomes a formal exercise. Now, extra ingredient we need in order to get a pure bosonic trace out of this path integral. Namely, suppose for simplicity that the Hilbert space, total Hilbert space, is a tensor product of a bosonic Hilbert space and finite dimensional fermion Hilbert space, which is nothing but this fermion Hilbert space. It's a Clifford module. Think of it as a Clifford module. And also suppose that quantum Hamiltonian H hat also decouples. It's a pure bosonic Hamiltonian tensor by identity operator in fermion space, plus the other term identity operator in Bose Hilbert space times some fermion operator. So that's the kind of simplification. Then in this case, what this path integral, which kind of we marked several times, this path integral, which can be computed by localization using this formula, then this path integral, which is a super trace of this product, and this product decouples as trace in Bose Hilbert space. That's one we want. That's the partition function, and some trace of a finite dimensional matrix, which, and in the simplest case, you can think that this trace, this HF hat is zero. When there is no fermion degrees of freedom in quantum Hamiltonian, then super trace of this observable is the actual trace. So that's the key formula, which is pretty simple. It allows to write the trace as a super trace in a trivial fashion, in fact. So you see, what is a super trace? So, for instance, for 2 by 2 matrices, super trace is trace of A, trace sigma 3 times A. But super trace of sigma 3 times A is a trace of A, kind of trivial tautological.
Leon?
Yes.
I have a somewhat provocative question, but now it looks like any trace, right, can be rewritten in that way. So you're going to localize.
No, because you see, HB comes from H hat. H hat is supersymmetric. Comes from
so
supersymmetry. And this supersymmetry should be such that all these conditions hold. So it's a very special. In fact, you should ask whether such HB exists.
Okay. I'll later ask that.
Yeah, but what I'll do next, I'll do examples, because this is a very
I have a question. Can I ask?
Yes, sure.
So this tensor product is Z mod 2 graded or Z graded? Means this H script H is script HB tensor product script HF. So what is this tensor product? Means Z mod 2 means usual supersymmetric or something else?
You write H script HF is a Clifford module. It is plus times minus. If you use this decomposition, you get decomposition of curly H plus plus H minus. But this is more. It's just decoupling of bosonic and fermionic degrees of freedom.
So this is usual tensor product.
Yes, yeah. Think of HF as C2. Think of simple example when HF, this one is C2. That's good enough. That's good enough. In some cases, it can be seen as C, for this is only for physicists, because there is some subtlety, because psi mu are fermions, but they are very special fermions. They are Majorana fermions, which have some anomaly when there are odd number of them, like one Majorana fermion, and so on. And there is a way to make them always even, because if our manifold is odd dimensional, you multiply it by a circle, S1, and then you add one more Majorana fermion, which doesn't interact with anything. And in this way, you can get H, curly HF is always a Clifford module of, because for that.
But Majorana is real.
Yes, exactly. When Majorana fermions are anomalies when in odd dimension. But this can be cured. And that's what we do. Because in the first example, I like to show Jacobi Poisson trace formula. And in this example, this fermion Hilbert space is just C. But you should think that this C is secretly tensor is multiplied by another C, which doesn't contribute anything. And so it decouples. So let's do examples. And that's the first example, which is really kind of fits this description. Because as Anton said, whether you can find such operators H hat B so that its trace is a super trace where you have capital H hat, by whether this is ever possible. Of course, it cannot be possible for all. It doesn't make sense. So it should be possible only in this case. So, and let's do one example. I think we have time for, and then I kind of mention what will be other examples. Right. So let's consider this is Jacobi Poisson. Our manifold is a circle, S1, and we consider a free supersymmetric particle on a circle. So its Lagrangian is this x dot square plus I psi dot. This is in physical time, Lorentzian or whatever, real time. Then the supersymmetry is very simple. Delta x is I psi, delta psi is negative x dot. T is physical time. And then the supersymmetry generator classically is x dot times psi. And then we can have a, so graded Poisson bracket is this, psi is I in Minkowski, so to say, space-time. Then the corresponding Hamiltonian is just QQ Poisson bracket, it's just P square, free particle on a circle, and corresponding Euclidean action is this x dot square plus psi times psi dot without imaginary I anymore. So that's kind of important that in Lorentzian signature you have I for real fermions. In Euclidean signature there is no I. And then the written index is given by this very simple fermion path integral, which is identically zero because there is a fermion zero mode. Which one? The simplest. You see, psi is periodic function on a circle. It has a constant term, chi. And this constant term disappears from Euclidean action. Euclidean action doesn't contain this term. And therefore, there is integral d chi, and there is no chi in front. Therefore, this capital I is identically zero for this precise reason, that there is a fermion zero mode. Now, what happens after quantization? Again, things are very simple. Chi h hat is just second derivative operator. Bosonic Hilbert space is L2 in a circle. We can compute the partition function. Partition function is given by this series in which we can recognize the value of Jacobi theta function on imaginary axis, where everything converges very nicely, right? So that's the trace, usual spectral trace. And then we, according to general scheme, we represent this partition function as a super trace with chi hat, and we'd like to compute this super trace using localization and get a different expression for this spectral sum. For this, we need to have invariant deformation V, which satisfies all these properties we discussed before, namely these properties. Properties 1 and 2 are satisfied, 3 is trivial, also satisfied, I'll just mention, but we need to satisfy these properties. Now, you see, it's kind of nice since you have delta x is, you have, you see, let's compute, for instance, delta chi. Delta chi is integral over psi, over delta psi. Delta psi is negative x dot. So when you integrate, you miss zero mode. So you miss zero mode. And therefore, delta chi is orthogonal to chi in a sense we discussed before. And then in order to write the invariant deformation V, which satisfies the properties, it would be of this form, psi dot times chi second derivative in time. Usually in standard equivariant approach to a localization, you always consider a deformation psi times x dot. That's the standard one, integral from 0 to beta d tau. This deformation is the deformation you use for Atiyah-Zinger index formula and so on. But this deformation V doesn't satisfy those conditions that we mentioned before. So this doesn't lead to localization because it localizes on constant maps. But this deformation satisfies the property because delta V contains second derivatives of fields, and therefore it's orthogonal. V and delta V are orthogonal to zero mode. That's what I am trying to say. And then the key is, so then the super trace is the limit of this path integral where you insert chi in here. And then this path integral from the formula for delta V, we see that the zero locus of delta V consists exactly of solutions of equations of motion. X double dot is 0. So it's no longer a constant maps. And then we need to compute this limit. Lambda goes to infinity, integral over tangent bundle to loops on a circle with reverse parity. You take chi, which is integral of psi over period, and then this Euclidean action deformed minus lambda delta V for large lambda. Then using this decomposition, that solution is this, we can pass from the loop space to the base loop space by getting the volume of the circle. Sorry, this I don't need. Sorry, how to get rid of this. Okay, so and then we do the following computation. So let's try to analyze it. So we need to compute this limit. Now we do some innocent replacement. Loop space by base, replaced loops by based loops. So we have, and then the key is that when you see the limit lambda, you multiply this by lambda and raise to exponent, then the limit for lambda goes to plus infinity, will give you a bunch of delta function. This is delta function of x. Delta function of x double dot coming from kinetic term, and fermion term gives you delta psi. Then you multiply them by Pfaffians from delta psi, and then you multiply it by, then you use the formula that delta fx is written as a sum over all zeros of a function f of x equals 0. Now it's delta of x double dot. It is equal to the sum over all classical trajectories, which are all classical trajectories, which x classical, which are written here, x classical, just linear functions of tau, divided by determinant, which is this, and times Pfaffian. Then you compute carefully all these determinants and Pfaffian. They give you precisely this number. And then if you compute the value of the classical action, Euclidean action, when x is x classical, you get beta in denominator. You get another sum, which is a sum over classical orbits, trajectories. So you compute the Pfaffian, this, compute this determinant. Of course, everything is zeta function regularized, so it's kind of trivial. And then also you use that, what is the dimension of a base loop space, quantum dimension? It's just -1. It's twice the value of zeta function, Riemann zeta function is 0. And as a result, you get Jacobi inversion formula, probably first written by Poisson, I think. Yeah. So this is Jacobi Poisson trace formula from this point of view. Left-hand side is spectral decomposition of the partition function. Right-hand side is explicit evaluation of the path integral. Now I just say what second example is. There is the most interesting example is Selberg trace formula, which we are writing down with Changha Choi. But in this paper on the arXiv, the second example was done in detail. Namely, what is our another example? Now suppose our manifold is a connected simple compact Lie group. Then, and Lagrangian is the following. Then just free particle on the Lie group. This is a kinetic term. This is invariant product using Cartan-Killing metric. Then psi same as before, but now nabla minus is not a Levi-Civita connection, is a flat connection on G. There are two flat connections, plus and minus. They have whose parallel transport are given either by left or by right translation. So, and this connection have torsion, but doesn't matter. Then the standard supersymmetry works in a more, basically in the same way as before. One needs to just use the basically algebra. So in terms of currents, you introduce instead of group elements, in terms of group elements G, you introduce a current belonging to Lie algebra. And then you can use the Cartan moving frame, so you write psi also in terms of Lie algebra. And then you get this simple expression for the Lagrangian. And then classical supercharge is cubic of this form, kind of. Then this is quantum classical Hamiltonian, just Hamiltonian of a free particle. Fermion degree of freedom disappear, and quantization of this Q gives you Q hat. It's a cubic Dirac operator of constant. Q hat is quantum Hamiltonian, which is Laplace operator on the Lie group plus extra correction. This extra correction is famous de Witt term, which people in physicists add by hand when they consider path integral on what they call curved space-time on manifolds. You need to include a term which contains depend on curvature. Here it comes naturally from supersymmetry. Just q square gives you correct de Witt term. This curvature is just dimension of group, 1/4 of a dimension of a group.
So this curvature is from this nabla minus or some other connection? Which connection is this from?
Curvature from Cartan. These are structure constants. So this is a curvature of a compact Lie group in canonical Cartan killing metric. Curvature of a metric written in this form: 1/4 structure constants squared. That's the curvature. And this also related to strange formula in Lie group theory, or Frondenthal strange formula, which is the same. So this is kind of elementary computation, which again uses some graded Poisson geometry. Then zero modes, and then heat kernel can be computed using representation theory. So our goal is to describe the heat kernel at some point. Little h belongs to Cartan subalgebra. Then using representation theory, we can also write as a sum over all representations or dominant weights, characters, and this form, which is a generalization of spectral. This is spectral description. Now the matrix trace is the corresponding integral, which we have no time to compute, is computed here. And I like to write you the final answer that the spectral matrix trace gives this expression. It's volume of a group, some constant like in a heat kernel. This is sum over gamma. Capital gamma is a characteristic lattice of a Lie group, so that Cartan subgroup of G is a quotient over this lattice. Then there is a product over all positive roots of this expression, and then you get exponent negative 1 over beta, which is exactly generalizes the right-hand side of Jacobi inversion formula. And this is spectral trace equals to matrix trace, gives what we call Eskin trace formula, written by a Soviet mathematician Eskin in 1964. And this he computed this heat kernel in this form using certain analysis on compact Lie groups, developing work of Berezin and other people. So that's another example where this localization principle works. And then the more complicated example is how one to get a Selbach trace formula, but I'd rather stop here. So I think that's it. So thank you.
Okay, thank you very much. Well, please, questions or comments?
Yeah, let me check in the chat. No,
So may I make a comment?
Sure, go ahead.
So it seems that that what you are explaining in words looks like fermionic symmetry of the Lagrangian, and your product of chi's seems to be like the gauge fixing of this fermionic symmetry. And because what you are doing actually, as far as I see, you take Lagrangian that has fermionic symmetry, and since it has fermionic symmetry, you could not integrate. The integral would be 0. So you have to fix the fermionic symmetry. And that's what your chi's mean. Because chi's are actually results of the gauge fixing. And I hope that the rest of your conditions would be closeness with respect to BRST operator corresponding to the gauge fixing of this symmetry. So probably this is a way to state your approach in the more elegant terms. What do you think about it?
Why you don't like it's Lagrangian is supersymmetric? That's the key. Of course, this interpretation probably is fine. But
No,
if you think that Lagrangian is supersymmetric,
but it is not enough.
that's
So
the key
here-
issue. If Lagrangian is not supersymmetric, you cannot do just gauge fixing. It should supersymmetry of the Lagrangian is a starting point. Then, of course, the integral vanishes due to the zero modes, and you just introduce them. You can probably interpret it as a gauge, but there is no gauge group. It's just supersymmetry transformation. That's
one moment. There are two things. One thing is a supersymmetry, for sure. But then there is another thing. That is, so you say, your action has zero modes. So it could be re-expressed in the form that your action has an extra odd symmetry, like shifts of these zero modes. And when you put these chi's down, it looks pretty much like gauge fixing of this extra odd symmetry. So in your theory, there will be the following, there will be two differentials. One is original supersymmetry that you started with. And the second would be BRST operator for the odd gauge symmetry. And what you are doing, you are just fixing this second gauge symmetry. So I conjecture that your conditions could be formulated in this way. So is it clear what I said?
so well, you see, it's kind of very. What's your symmetry? You're saying psi goes to psi plus chi?
Yes.
Well, it just then you say just reformulation. Just it's a shift. Psi goes to psi plus chi, right?
Yes, but what I propose is that using this reformulation, one can construct generalization of examples that you have.
It's the same, it's just reformulation. That's I don't quite understand. Maybe you can write to me or tell me something. Yeah.
Okay.
Just reformulation. I understand that symmetry is psi goes to psi plus zeros Fourier coefficient. Right?
Okay, I'll write to you.
Mhm.
Okay,
Thank you.
perfect, thank you. More questions or comments?
Yeah, I have a question because I didn't understand this. That's why I'd like to ask the question.
Sure, go ahead.
So this nabla minus, this connection you put on this Lie group, it's not a Levi-Civita connection that I understand. But is there any relationship between this curvature and this nabla minus? Means it's a bit mysterious to me why you introduce this nabla minus and then how it gives this curvature scalar, this term, dV term. So maybe I didn't follow it.
You see,
well.
you see, there are two things. This nabla minus is needed to have this Lagrangian L written in this form. Nabla minus needed in order to decouple bosonic and fermionic degrees of freedom. So this formula only makes sense when you put here nabla minus. If you put here Levi-Civita, you wouldn't have such decoupling because psi doesn't depend on point on the Lie group. Psi belongs to Lie algebra. You see, psi belongs to Lie algebra now. Instead of, we have psi mu d by dx mu at each point G on the Lie group, but these are psi a. They carry Lie algebra indices. And so you need this flat connection to decouple degrees of freedom, but then this curvature form comes from structure constants of Lie algebra, which don't depend on a choice of a connection. This is a
Leon,
and
may,
this is the
may I offer a different answer? The one that you already spelled out during the talk, right? The curvature is determined by the metric, and then the connection, you can choose whatever connection you want, Levi-Civita or not Levi-Civita. The curvature is still the same, right?
right,
So
right,
it's
exactly.
a kind of two independent questions. What is the connection, and the curvature is something which is solely determined by the metric.
Right, and this choice, but also this choice of a connection is important so that H hat doesn't contain fermion degrees of freedom. So we have a supersymmetric transformation. Let's look at this cubic Dirac operator, so to say. Then its square fermions disappear in the square.
So is it a good way to say, actually, on a Lie group, the Levi-Civita connection is not a good choice? I don't know, but whether one can, whether one is allowed to say it, but I think that's true.
I think this operator was used by Constant and Bismuth, and I think maybe in one of the papers I've seen Bismuth was doing similar computation, that Q square really gives you this H hat, Laplace operator. Yeah, you're right. Levi-Civita is not a good choice on a Lie group. Although you use the metric, you always use the metric when angle brackets are Cartan killing metric. In all these formulas, angle brackets denote Cartan killing in a product, in a Lie algebra. Just it's, but the metric connection needed on fermions, you can put any connection here, if and only for flat nabla minus or nabla plus, you get this decoupling.
Okay, thanks a lot. More questions or comments? So when should we expect the Selberg trace formula?
Well, we're working on it here. It's more complicated, but it's kind of interesting.
Okay, people, if I don't know, if there are no more questions or comments. So then let's thank Leon again. Thank you very much.
Thank you. Thank you for inviting me and for asking questions. Thanks a lot.
Yeah, so thank you everybody for participation. And so we have now a winter break. I wish those of you who have vacations to have nice and relaxing vacations in the end of that year. And we restart towards the end of January, as I mentioned, January 26th. This will be the first Global Poisson webinar of 2023. So thanks a lot and bye-bye.
Bye-bye. Bye-bye.